Hi, I'm Anthony Kendall. I'm a research professor here at Michigan State University. Our work falls into two separate pieces. We're expanding and improving the nutrient source maps, and I will give you an overview of that in a moment. And then we have a nutrient transport aspect where we're using statistical models to move those nutrients from their point of application on the landscape to their ultimate fate in stream or nearshore waters. The slide here shows in the earlier version of this that was incorporated in the first tipping points iteration of the tipping points planner, where we had 6 sources for nitrogen, and those are labeled A through F. Atmospheric deposition, so that's nitrogen that's loaded to the landscape from the air, both in rain as well as dust that falls out. So you would expect that it's higher in areas where nitrogen is being put into the atmosphere from industrial or agricultural uses. Manure, so manure is from farm animals being applied to agricultural fields. It's hottest or brightest near large sources like confined animal feeding operations. We have chemical agricultural fertilizers, which are the single largest source. They're what most people think of when we talk about nitrogen being put on the landscape. But they end up not being the dominant source. They're just the largest source. These other sources really do add up. Septic systems is shown next, and you saw a larger version of that graphic on the previous slide. Chemical non-agricultural fertilizers are also important. They're put on things like golf courses or lawns or commercial properties. And each one of these, there are estimates of how much is being loaded by county that are from other sources like the US Geological Survey, that we then go through a detailed process to turn that into an explicit map of each individual. At this case, this is 30-meter pixels. And then finally, we have point sources. So those are traditional loads put directly into stream systems from permitted pollution discharging sources through the NIPDES database. We've added to this, as part of this newer version, we've added to it nitrogen fixation from crops like legumes, soybeans, things like that, which were not a very large source in Michigan originally when we considered this, but as we expanded to the Great Lakes Basin, we started to encompass places that had quite a bit more soybean production in particular. So that's going to be one primary enhancement. We've also done a number of other enhancements, including how to handle manure, because quite a bit of, for instance, the nitrogen that an animal actually excretes and is originally captured, quite a bit of that nitrogen actually leaves the manure storage facility. Maybe it's a composting facility or a storage lagoon, actually leaves through atmospheric nitrogen. And so we've come up with estimates of that. So we're working on strengthening the science behind these nutrient maps, as well as scaling them out to encompass the entirety of the US side of the Great Lakes Basin, so that watersheds throughout the Great Lakes Basin can make use of them. We have similar maps for phosphorus, although there's no phosphorus fixation, so that these 6 sources represent the individual phosphorus maps. The next aspect that I wanted to discuss is nutrient transport. So once we have these loaded to the landscape, that is an important part of managing nutrients. We need to know what's being put on, because obviously if we want less out, one of the major things we can do is put less on to begin with. But the other aspect that's important is to ask questions about, well, where should we target our efforts? What proportion of the nutrients that are being applied actually even make it to the stream? Because obviously the landscape can use those nutrients. Plants take up nitrogen, they're harvested and then hauled off. Nitrogen is lost to the atmosphere, like in the manure case, for example. Nitrogen is taken up in streams and converted both to atmospheric nitrogen as well as to the community within that system. So we need to be able to transport our nitrogen and phosphorus from their point of application to their ultimate water body that we're interested in understanding the water quality. So for this, this slide here just shows on the right, this is a paper that we recently published. It shows a graphic illustrating the sources of these, the green sources that I've been talking about. And then each one of the red arrows illustrates an uptake or a loss along a transport pathway. So transport pathways might be overland to the stream, or they might be underground through the groundwater system. They might be through a septic tank and then a septic plume, or they might be through agricultural tile systems, each of which has unique properties in terms of nutrient uptake. This model attempts to describe each of those by using measured data and then fitting a number of underlying landscape parameters, fitting a statistical model with those landscape parameters to the measured data. So this is a typical type of correlation approach for statistical modeling. So the model does a good job of representing how much nutrients are moving through the system, which gives us confidence to be able to make products like a map of the percent of nitrogen or phosphorus from each and every point in the basin, how much actually makes it to the stream. And some of those sources actually load differently. When you put sources in the ground in a septic system, it transports very differently than if you put that same amount of nitrogen on the surface. And so the model accounts for those different transport pathways with these different uptake parameters. So with this, we hope to make the information about nutrient loading more valuable so that people can make better decisions about where to target their efforts, given the various other constraints that land use planners might encounter along the way.